Hello everyone, welcome back to another video for the series. I'm Enoch Yu, and today I would like to share a it's not like that famous but very useful theorem in geometry. I think it was first proposed as a problem and then it became a lemma. It's called 3 tangent lemma. Um, the reason why I brought this, I would say, problem today because we're actually going to use this lemma in the next problem that we are going to solve today. So, next problem that we are going to solve in the next video. So that's why I thought it would be good to prove it, because if I just use 3 tangent lemma, it would not be like complete solution for the next video. So that's why I brought this lemma. So what this lemma says is, hey, I think we need to draw first because it's sometimes easier to draw. I mean, what am I saying? Sometimes easier to see after drawing. So say we have a big triangle. It's going to be an acute triangle. Um, and we're going to draw a few horizontal lines. Oops. Uh, from here to say here, this looks horizontal. Yeah, okay. The next one is going to be from here to here. Yeah. So obviously this point right here is an orthocenter, and we're going to draw a circumcircle that passes through 2 points, 3 points here. Um, uh, yeah, like this. Then you're also going to draw a midpoint. So let's say this point right here is our midpoint. Kind of looks like it. Yeah, so that's our midpoint right there. We're going to connect this one, this, another one from here to here. And we're going to draw one last line, goes from here to here. Let's make that shorter. Oops. Yeah. So let's give names. Let's give names to these some of our points here, so that we could actually write our lemma. And let's call this A. Let's call this B. Let's call this C. And this is midpoint, so let's call it M. ABC. D, E. Let's call this orthocenter F. I mean H. Yeah, so this is basically it. So the lemma is saying for an acute triangle ABC, for an acute triangle ABC, let CD let CD and BE be the altitudes to AB and AC respectively. If M is the midpoint of BC, DM, ME, and a line through H, orthocenter center of triangle ABC, and the line through AB and line through H parallel to BC. BC are tangent to the circumcircle of ADE. Yeah, this is quite long. So basically what it's saying is that following this construction method, these three red points are tangent to this circle. So we're going to prove it today. How should we prove it? So we're going to use few of the properties in geometry, and I'm not going to explain all of them here because I think I did explain some of them already in my previous videos, so please check them out. Okay, so how do we prove that these red lines are all tangent to this circle? Then let's first chase some of our angles. So we know that this is 90 degrees. This is 90 degrees. That means quadrilateral ADHE is cyclic, meaning H is on the circumcircle of ADE. So that's what we know. Yeah. Okay. Then the next thing that we can know is okay, so from here, let's try and use some of our properties. Okay, so notice that this is a right triangle and this is the midpoint obviously these 4 lines segments are all equal in length. I think that's quite obvious why they're the same length. Just draw a circumcircle. Yeah. We're going to use this property right here. And our question is, how should we use it? How can we use this fact? Um, so, wait, we already proved that the red one, this red one is, so this one is already tangent to the circle, right? Because this means h is, so trying this one equals, they are congruent to AH, meaning AH is the diameter. So notice that this is 90 degrees and AH is the diameter, and this is parallel to this one, so this should be 90 degrees. But we know that this is 90 degrees by construction. But to notice that, we could know that this is tangent to the circle because it is the diameter. AH is the diameter. So yeah, so we know that yeah, so we know that this line right here is already parallel. So we completed the proof for this one line. We only need to look at these two. And we only need, notice that we only need to look at one because the whole situation right here is symmetric. So let's, without loss of generality, let's look at D generally. Yeah, let's look at D. That way we could just say it is symmetric for E. The whole process is symmetric. So let's look at D. How do you prove that this line is actually tangent to the circle? I think one way to do it is to use a very famous property in geometry, and it's this one. No, draw this line. If uh, yeah, if, let's see, if this angle, where is it? If this angle equals this angle right here, then we are done, because this is an if and only if condition, and we already proved that in many of my videos, so please check it out. Let's use red and let's use blue. Okay. Oh, sorry. Oh my goodness. Like this. Yeah. This one, this blue is obviously equal to this one because it's an isosceles triangle. Then how do you prove that this angle is equal to the red one? I think there are a few ways to continue from here, but okay, so let's say red equals 180 minus C minus B. And this is equal to, what is C? C is this one, because this and this are equal to each other. 180 minus B minus MEC, angle MEC. And 180 minus MEC minus B. So if AED equals B, then we're done. How do you prove that this and this are equal to each other? So if this angle and this angle are equal to each other, then we're done. Here, I want to show my personal proof on how I figured this one out, because I actually figured it out while solving a problem related the next problem that I'm going to share in my next video. Yeah, so please check that out. Okay, let's call this angle green. So notice that this angle, no, should we just call it alpha? If this is alpha, obviously this is alpha, same chord. Okay, so if this is alpha, then what else do we know? So here we know that this angle is also alpha, right? Because just use similar triangles. This is 90 degrees. This angle, they share the same angle, so this is alpha. So if this is alpha, they are parallel to each other, so this angle right here is alpha. So this angle is actually equal to alpha. So I should just call MEC beta for convenience. Then let's erase this. Beta equals 180 minus alpha minus beta, and this is obviously blue. So red equals blue, and therefore DM is tangent to this circle right here. And we could do the same for E, but everything reverse. Not reverse, but using this side of the angles. And yeah, so just call this alpha, call this beta. I think that should solve it. Then, wait, if we call this alpha, then if you call this one alpha, we call this alpha, and we can continue like that. And that completes our proof. Yeah, so this was it for today. This is quite useful lemma. I really hope this problem appears in the KMO, because I think it will be useful. So I think this lemma will come handy if we have orthocenter and a triangle and a circle with the diameter as a length that connects a vertex and the orthocenter, and a midpoint from the opposing side. So I think those conditions would be really important, and looking at those information would be crucial to see if we could actually use this lemma. So thank you so much. Oh wait, sorry. One last thing. I think we need to prove it during the test, because this is not like a well-known lemma, I would say. So yeah, but it's not that difficult to prove, just angle tracing, and that's it. So thank you so much for watching this video, and tomorrow I'll come back with another very fun and interesting problem related to this lemma. Thank you, and see you tomorrow. Bye.